It's my pleasure to present Professor Gilles Lubineau. He's a professor in mechanical engineering and associate dean of the Faculty Science and Engineering here at KAUST. He's also a founding professor, and he leads the laboratory for mechanics of composites for energy and mobility. Today, he will present supersensitivity, resistive, and capacitive strength sensing.
Good afternoon, everyone. So it's a pleasure to be here. Thank you very much for the nice invitation. Thank you, Eric, for inviting me. Because I think it's a community that is a little bit different from my community, but I think it's a good way to know each other and to know better what we are doing. So I'm Professor Gilles Lubineau. Thank you for the nice introduction. So as you were explaining, I'm running the mechanics of composites for energy and mobility. So since we don't know each other, I will start by giving a few words about this lab that is here at KAUST in Building 4, but you can visit whenever you want if you are interested. So this lab started a few months ago, but it is, let's say, it comes from the composite lab that I started here in 2009 when I came at KAUST. It's an evolution of this lab that we reshaped 6 months ago when we changed, when we are focusing now 100% on energy and mobility. So that means if you look at my team, it's between 15 to 20 people. And honestly, usually we go to conferences that are quite different from your conferences. We are clearly not from the same community, but this is my world. This is all about cracks and delaminations and the way you are going to break carbon fibers or glass fiber reinforced composites. So, these materials. So this is what is exciting us, looking at the propagation of cracks and how cracks in laminates are going to bifurcate to create delaminations, how you would create damage when you have impact in composite structures and so on. So at least I'm sure that you will have seen one crack in this presentation that is more my background. And now, so I will explain. So if you look at the team, so this team has something that is very specific. It's a very multidisciplinary team. So that means we look at composites, but we look at composites from all aspects. So we look from the experimental point of view, but also from the modeling and simulation point of view. So it means 50% of the team is experimental and is computational mechanics. And what is very specific to our group is that every single project is always looked from the different angles with people working from experiments and simulation at the same time. So if you come to visit the group, you will find people in a background in theoretical mechanics, computational mechanics, damage and fractal mechanics, material science, multifunctional materials. So this is very diverse. And this is why at some point, it happened that we have been interested a little bit in flexible electronics and soft robotics. So we came to this, even if our background is more about structural composites, we came to have some projects typically on conductive polymers. So we have pretty much a world record when it comes to conductivity stiffness in terms of PSS-based conductors. So these are wires that we created that you can use to make flexible electronics or systems like this. We happen also to have some project about distributed sensing, integrated sensors for non-contact sensing or distributed pressure sensing, things like this. We worked in this not because we are from the sensing world at the beginning, but more because we come from the composite side and there are some composite technologies that we can use in this. And recently we have been interested into two things. So before I go to the core of the project, I want to show you a little bit what we did recently in soft robotics. And especially we have been interested into one thing, but the first thing that is about having some concept for full electrical actuations with large motion. So this is something that we did over the past 3 years. And what is the idea in this? The idea is that when you go to the soft robots that you find today on the market, I mean, not all of them, but let's say the ones that are performing or the ones that are the most widely used, they are all pneumatic actuated. That means you are using air pressure usually to actuate them. And these have a lot of limitation because this requires a pressurization system to get the high pressure air in your soft robot. And this comes with wiring systems, so bulky and complex wiring system that might be complicated. And we wanted for us to be able to achieve the same performance, but something that is fully electrical. That means you just put two electrical wire, you power your system, and you are going to get a large displacement. And this is extremely difficult to do with electrical actuation, because if you look at electro actuators that exist today for soft robotics, they are all about very small amplitude. So if you want to get a large motion based on electrical actuation at low power, it's extremely difficult to do. So for this, what we developed, of course, is a concept that is based on phase transition. Okay, so phase transition actuator, why we are doing this? Because, of course, if you want to get a large motion, something that is moving over a wide a wide range. I mean, the best thing is to take a liquid phase and then to vaporize the liquid phase to get a gas, right? If you do it, you get a large change in dimension. You get a large change in volume. So that means that we generated a family of actuators in which basically the multi-physics is very simple. I mean, you input electrical power. The electrical power is going to generate some heat by Joule heating, and this heat is going to vaporize the liquid and induce actuation, right? So this is typically a project that we did recently on this. So that means that this is a fully electrical power, just 2 electrical wires, 30 watts, by vaporization of the fluid that is inside. So that all the engineering here is about the electrode that you put inside the actuator to get a good efficiency of your vaporizations, to get a good electrical efficiency. So this was the first family of project that we were doing on this. That means being able to have large amplitude, soft actuators, only electrically driven. And then, of course, when you look at this, the shape of this motion is 100% guided by the stiffness of the membrane that you put around this. But here you get a bending in this direction because here you have a stiff membrane and here you have a soft membrane. So, of course, you are going to get a bending if you pressurize this. So it means the second part of this project was about being able to control and have reversible actuation. That means doing exactly the same thing that you do in worms. That means that you have a pocket under pressure. You make an hydrostatic pressure that is coming from your transition from liquid to gas. And then being able to control at every point of the membrane the stiffness and to change the stiffness at every point to make sure that you can change the actuation, right? And this is also something that is extremely difficult to do because if you want to do this, in fact, you need to be able to have locally a change in stiffness. I mean, if you are below 1 to 50 between the soft and the rigid phase, you are not going to control anything. So you need to have something that can be very stiff or very strong depending on the signal that you are putting in this. So for this, we generated a family of fibers that is a composite fibers, in which you have two phases, one stiff part and then one part that can be melted, that can be controlled by electrical melting. So it's based on gallium. And that means this kind of fibers, they can be either very stiff or very soft when you induce the melting of the gallium. And this, if you put this inside the skin of this kind of systems, but here you have some fibers in this skin, and then depending on the point, you activate or not the melting of these fibers, and then you can control the stiffness and make a distribution of stiffness in your robots, and then you can change a little bit the shape just by controlling this. So these were two concepts that we introduced at the beginning on this, and the idea was always the same: having something that at the end is only electrically controlled, either for the actuation or for the stiffness change. Everything this just works only with electrical power and low electrical power. Now I will come to what makes the core of the presentation today. That was the third challenge, but is about being able to measure the strain in this kind of systems. To measure the strain with strain sensors, with wireless strain sensors that you can put on this, and that you can interrogate, that are going to work at large strain, that are going to be very sensitive to the strain, and you can interrogate in a wireless way. So the way we are doing this, actually we have, it's something that is not that easy to do because what we want to do is to have a family of RFID sensors. So by the way, what I present here, I present this here in the context of soft robotics, but this is also something we are interested in developing because this is one way for us to develop systematic monitoring of composite structures. So there is a full story behind this, but if you are interested more about the composite side, we can discuss on this afterwards. So the way we develop this is that we are developing RFID patches. So that means resonating system, LCR system. If you have a resonating system like this, so you can interrogate it by electromagnetic coupling. And you know that when you have this coupling between the interrogator and the sensor, I mean, there is a resonance frequency that depends on the capacitance of your system, right? And the way a capacitive sensor usually works is that when you change the capacitance of the sensor, when you change the capacitance here, you get a shift in frequency and you measure this shift of frequency. And if the change of capacitance is related to the change in strain, I mean, your shift in frequency is a way to monitor your strain, right? The main problem is that if you look at all the capacitive sensors that exist on the market, they have a very small gauge factor. Not extremely small, but it's close to 1. It is only due to the geometrical change due to the extension of the sensor. And this makes a gauge factor that is close to 1. Small gauge factor, that means that you have a very small shift in frequency on that curve, right? And if you want to have a good wireless monitoring for our system, we want to be able to have a big shift here. So we want to increase the gauge factor. So the question comes to how do you design patches like this, in which you have a capacitive sensors with a high capacitive gauge factor. That means a high change in capacity when you have a strain. So you can measure something that is relevant. So for this, we are using our approach is to use a transmission line approach. So that means that we are taking a capacitor. So this is your capacitive part, right, with two conductive electrodes, and in the middle you have the dielectric. And what we do is that we make these electrodes very piezo-resistive. That means the resistance of the electrodes can vary a lot with the strain. And this is what makes the thing work. Because if you do this, at low strain, let's say you have an electrode that is almost perfectly conductive. So, I mean, that means your electrical signal, your interrogation signal is going to penetrate the sensor. But then as soon as you apply some strain to this, and I will show you in 1 minute that this piezo-resistivity is coming from quarks, as soon as you introduce some strain, the resistance of these electrodes is going to increase a lot. And due to the increase in resistance, you will limit the penetration of your interrogation signal, and the effective length of the capacitance is going to decrease and will be a function of the frequency, but mainly will be a function of the strain. That means when you increase this, in fact, when you increase the strain on these sensors, you reduce the size, the effective size of your capacitance. And this is a way for us to have a change in capacitance that is much higher than the classical geometrical effect that you see in capacitive sensors, right? So this is really the idea. If you want to have something like this that works, you need to have at the beginning electrodes that are very piezo-resistive. That means you need to be able to design electrodes that can sustain a very large deformation. And then during this very large deformation, you can have a very large change in resistance. And this large change of resistance is what is going to make your capacitive sensor work. So here you have different approaches. So this is pretty much the goal of what we want to do. So that means at the beginning, if you want to make it work, you want to have electrodes that will have a piezo-resistive gauge factor that is very high, let's say above 100, or let's say at least between 50 and 100 compared to what is on the market. You want to have something that is very stretchable. You want to sustain at around 100% or 50 to 100% of expansion. And then you want to have a relatively linear response, because if you want to invert your equations and to understand your system, it's always good to have a relatively good linear response on this system. So if you want to introduce, so now the point, if you understand from the beginning, we go from wireless to sensitive capacitive sensing, and this comes to having highly piezo-resistive electrodes. So how do you introduce piezo-resistivity in material? Piezo-resistivity, that means that the resistance of the material varies with the strain, right? This is a definition of piezo-resistivity with hands. How do you introduce piezo-resistivity in material? So there are different, very classical approaches to do this. The first one is to take a cloud of conductive nanoparticles. So you take a polymer, you take something that is insulating, and you put inside a cloud of wires that are conductive, right? And then you assume that if you go to this wire, so when you put enough particle, you get what you call percolation. And you have a percolated network that is a black network here that is going to make the conduction of your electrical signal. And the conduction is mainly dependent on the interaction between the particles. And what you assume is that at the junction between the particles here, there is, to make it simple, you can assume that there is a kind of equivalent resistance. Of course, it's an oversimplification, but you can assume that there is a kind of equivalent resistance that is going to be exponential with respect to the distance between the particles. That means as soon as you separate a little bit the particles, the resistance is going to increase a lot. And this is what gives the geometrical perturbation of your network. It is what gives the piezo-resistivity, right? So, of course, this is something that has been used in all the piezo-resistive sensors that you know today. This is something that gives a very high piezo-resistivity when you are close to percolation, because when you are close to percolation, there are very few particles that are touching together. So as soon as you perturbate something, you increase a lot the resistance. This is something that gives a piezo-resistivity, but much smaller when you are in well-percolated networks, because you have well-established percolations and you have a lot of connections. So the piezo-resistivity is less intense. So this works, but clearly it doesn't give a piezo-resistive effect that is high enough. It has been used, for example, on coating on nanoparticles on PDMS, on different kind of silicones, right? And here you have a paper, for example, to 2011, where they show that if you make a coating of nanoparticles on a PDMS substrate, but you have a change when you make extension of this, you have a change in resistance. that exist. You have a piezoresistivity, but it's very small here. That means you get a gauge factor that is very small. You get a big stretch, but a very small gauge factor. Another way to use exactly the same concept is to use, for example, clouds of metallic nanoparticles. So this is what you call, for example, nanosensors, in which you have metallic nanoparticles here that are touching each other on a polyimide substrate. Or if you do this same concept, you get a high gauge factor. It's around 30. But of course, you are on a polyimide substrate. So as soon as you stretch a little bit your substrate, you separate the particle. So you have a very small stretchability. So that means there is no solution. Either you have a small gauge factor and big stretchability, or high gauge factor and small stretchability, but there is nothing that can sustain a high stretchability with high gauge factor. So our approach to be able to do this, to be able to reach this super high sensitivity, is to use at the beginning cracked films of CNT. So we are going to use film of carbon nanotubes, and we are going to play with the piezoresistivity of the quarks that you can introduce inside these films. So same thing, introducing quarks in material to get piezoresistivity is not something that is new. You have at least these two papers. So you have this paper in which you take a forest of carbon nanotubes, and that you deposit this forest of carbon nanotubes on a PDMS substrate, and you pull on this. Here you get a piezoresistivity sensor because you separate the tubes. But of course, you get a small gauge factor because you work in the transverse direction to the nanotube. So you get a conduction, but you get a high resistance at the beginning. So you cannot expect something that will be very piezoresistive. And then another very well-known paper is this one. So it's a metallic coating on a PET substrate. But same thing here, you introduce quarks in the metallic coating. Here you get a very high gauge factor, more than 2000, because you directly play with the opening of the quark. So if you have a quark that is touching, as soon as you separate it, you are losing the conductivity and your gauge factor is increasing, right? But of course, since you are using a metallic coating, as soon as you separate the quark, you are losing the conductivity on a PET substrate. So same thing, same dilemma. I mean, either you are very stretchable with low gauge factor or high gauge factor, but you are non-stretchable. So here I will show you two technologies. If I have time, I should have time. So one that is based on using CNT paper with random quarks. Maybe I will skip a bit the mechanism, and then I will show you how you can make it work even better if you pre-engineer the pattern of quarks inside your electrodes. So first thing, electrodes with random quarks. What are the mechanisms? What is the performance? And what are the key features? So here again, what we engineer now, it's only the electrode part of the capacitive sensor that is going to come in your wireless system at the end. So what you do is that you make what you are doing here. I will go quickly on this because it's not the point of the community today, but you make CNT paper, so you can make it, but any technique. You make filtration of a bath with suspension of nanotubes, for example. At the end, what you get papers of CNT that are pretty much randomly aligned in plane. You filter this, and then you can get strips like this that are strips of CNT that are conductive strips, right? So it's only this strips is already piezoresistive, but it's through the normal network of nanoparticle. And then what you can do is that you take these conductive films of CNT, and then you introduce quarks in them. So you activate them. That means you pull on them, and then you quark the film. So you introduce what you call transverse quarks and delamination. That is separation between the CNT and the PDMS. So this is the activation phase, and then you unload. So that means here you come back to your initial electrode, but without residual strain. You just unload the system. The quarks are here, but they are closed. And then what is very interesting to observe, so you can do it with different thicknesses, depending on the thicknesses. I will not go in detail on this today, but depending on the thicknesses, you observe all the classical mechanics of thin films. That means if you work with very thin films, you get quarks that are not percolated. If you go to thick films, you get well-percolated quarks with low density. Everything is very compatible with the classical mechanics of thin films. And what is interesting is to see this. That means now if I take a film of CNT paper with quarks like this, if I apply a strain on this, so if I go from 0 to 50% strain to 0, and if I take one of these thicknesses, for example, if I take a 90 micron CNT film at the beginning, what you observe is that you have an initial resistance that is around a few ohms. And then when you start to increase the strain, you have a very huge increase in resistance that is going, let's say here to 10 megaohms, but you never lose the conductivity. You always have a conductive system. but you have a very huge change in resistance, and then you come back to the beginning, to the initial value when you reduce the strain. Okay, so this is a super high piezoresistive film, but of course, you can explain the mechanism based on the different step of separation of the CNT paper. That means at the beginning, when the strain is low, you have a direct conduction through the CNT paper because, of course, all the CNT are bridging together. And when you start to increase in the second step here, the resistance starts to increase very quickly, and this is due to the fact that you are breaking progressively the bridge in the CNT paper, and you start to have conduction through the interface on the top. And what really gives the high piezoresistivity, that means the high resistance here, is when you have separation of the fragment, but you have conduction through the delaminated interface. You can show this. In fact, the delamination is what makes things work in this kind of. But what is important is that with this, I will skip this. You are not so much interested in this. Well, the delamination is important. I will not have time to discuss it today. But what is important is that if you look at this, you get system with a piezoresistive gauge factor, but can have a gauge factor up to 10 to 6 with a stretchability up to 20-30%. So you have a very good gauge factor, but the response is highly nonlinear, and the stretchability is limited. Here you see that you still don't get the 100% stretchability what you would like to get for your application. So that means we bring the piezoresistivity, but not the stretchability and these things. So how can we restore the stretchability and everything? You can do this now by engineering your quarks. That means in this first part of the presentation, the quarks, they are what you call quasi-random quarks. That means you let them to the micromechanics of quarking of your film. But now you can design your quarks. You can decide where you are going to put your quarks. So this is in 2 slides what I want to show in the second part. What we are going to do now is that instead of quarking the film just by pulling on the film, what you do is that you decide where the quarks are going to happen. So the way you do this is that you just make notches, right? So you come with whatever you want, but something that is going to make an imprint. So you force the localization of your quark. So here, typically, we do it with a laser beam. So you come with a laser, and then you plot the initial position of your quarks, and then you are going to get quark propagation through the thickness at this different point. So you get a pattern of quarks that can be much more controlled and much more organized. And then when you do this, so you get films now where the quarks, you see, they don't look the same at all, right? But you decide at the beginning where you put your quarks. So you can completely engineer this, and you can get density of quarks that are much higher than the limit that you get with classical fractal mechanics, because you can initiate your quarks with a smaller step. And you can see that when you start to increase the number of quarks and the density of quarks, you can operate at level of strain that are much higher. And here you go to level of strain that are up to 100%. And now you get films that means you can reach, by doing this, you can reach maximum stretchability on this system that goes up to 150%. And you get a very good linearity of your sensor. This is strain that is increasing. And when the strain is increasing, this is the resistance of your electrode. So you can get a very good gauge factor up to 40,000, very high, with good linearity and good stretchability. So this is a little bit the story behind the engineering of these piezoresistive electrodes for capacitive sensing. And then at the end of the day, what you do is that you are using these electrodes, and these electrodes, you put them in a capacitive sensor to use the transmission line concept that I was explaining at the beginning. And then what you can do is that you can measure the change in capacitance of this kind of structure as a function of the strain for different interrogation frequency, right? So you get the capacitive gauge factor. And what you see here, you can get gauge factor between 10 to 40 relatively easily. So the gauge factor is going to depend on the interrogation frequency. But this means that now you have a capacitive sensor that you can trust and implement in an RFID system to make strain measurement in your stretchable systems and to have passive monitoring of your system. So this is pretty much the story around this. So that means we get integrable. This can be integrated into LCR resonators. So this is with CNT papers. Hussein, who is here, is doing now exactly the same thing with metallic systems. So it's a global technology that we are developing in the lab, not only for soft robotics, but also for composites. So just as a conclusion, so that means we develop, let's say, ultra sensitivity and high stretchability in piezoresistivity by using a special engineering of CNT papers in this work. The sensing mechanisms can be explained by the sensitivity of the local delamination in the paper. You can integrate it into capacitive sensors And these films are going to allow ultra-high capacitive gauge factor in stretchable systems, so you can have an efficient wireless monitoring for our soft robots or other applications. So these are a couple of publications that are related to this, either about the manufacturing of the films or the application of the different system for soft robotics, including the electrical actuations or the stretchable fibers with tunable stiffness that you can use for controlling the skin stiffness and things like this. So it's more here again, soft robotics is more something that we do in the team more as a side activity. It's not central to us, but I think sometimes it's a good playground to have applications of composite concept. Well, I think that's it. I'm just in time with 3 minutes. So thank you very much for your attention. If you have any questions, you can always reach me on this email. This is a website for the team here. So you are welcome to visit us anytime, Building 4, Level 2.
Thank you. Thank you a lot, Professor Gilles, for the fantastic presentation. I honestly consider the topic fascinating. We have a question in the chat. Rawan is asking if the carbon glass electrode is useful in reducing resistance.
Carbon glass electrodes useful in reducing. What do you mean by carbon glass electrode?
Maybe I will ask her to specify better the question. Thank you.
So what is important is that you get an electrode with a relatively low resistance at the beginning, because you don't because if your resistance at the beginning is big enough, you are not going to activate this frequency dependent. So what is important is that your electrode at the beginning has a resistance that is relatively small. So the CNT papers is good for this. But what is also important is that it will keep a conductivity even if you introduce a lot of damage mechanisms in this. So most of the system in which we introduce quarks, for example, if you take metallic films, as soon as you introduce a quark, you are going to get a high increase in resistance. But this is going to increase so quickly that you cannot monitor 10%, 20% of things like this. But very quickly, you will go to a perfectly insulating system. So what is important is to make sure that you have something that can relatively progressively lose the conductivity from 0 strain up to 100% strain. That is a little bit more complicated to do. So that is why we are using CNT paper in this application.
Thank you a lot for the answer. I know when you work in the state of the art, the fabrication process, it becomes difficult. When you're working in micro scale or even millimeter scale, I would like to know if it is actually an issue in your research.
There is a difference between what is an issue and what can be scale up and what can be made at large scale and everything, right? So this is, if you look at these sensors, for example, I show here some CNT papers and everything. At the end of the day, if I would like to make, let's say, an operational system and commercial system based on this, I will certainly not use CNT papers because for reason of cost and different reasons. But the concept itself can be scalable. We are working with Hussein now on the same solutions based on metallic structures. Here again, for the proof of concept, we are using technology for the fabrications that are very focused on making a few prototypes and everything. But we always have in mind the fact that behind this, if this kind of RFID tags and everything are working, you need to be able to print them at large scales with a series of 10,000. So this is always part of the things, right?
Thank you. Thank you a lot. Okay, if we don't have more questions, I would like to thank Professor Gilles one more time.
Thank you.